Hi everyone. So in this video, we're going to be talking about the first part of the fundamental theorem of calculus. So we'll see that there are kind of two parts to the fundamental theorem of calculus, and they're both really important. But the first part is going to be a slightly more conceptual kind of statement, and that's what we're going to be covering in this video. In the next video, we'll cover the second part of the fundamental theorem of calculus, which is a more kind of practical theorem that will help us to learn how to evaluate all sorts of different types of integrals. So the first part is really important because it just conceptually underlies a lot of the stuff that we're going to be doing this quarter, but we'll see that what we get to in the next video is going to be, you'll probably see it as more important because it's what we'll be using all the time. But this stuff, like I said, still important, still interesting. So in the previous video, we introduced this idea of an area function. So an area function is a function where your input is telling you the top bound of your integral. And so one example that we did in yesterday's video was the function f of t is equal to 3. So if you take a function where you're taking this top bound, so this number x, and you're kind of sliding it back and forth, that's your input, right? So you're plugging in different numbers for x. And then what's the output of the function? Well, you're just computing, what is going to be that area when I put that as my top bound. So for example, if you plug in 1 for x, then you're looking at the area from 0 to 1. If you plug in 2, then you're looking for the area from 0 to 2, and so on. So we saw that in the previous video, we could come up with a general formula for a of x. So in the previous video, we found that just kind of using geometry, using the fact that the shape is a rectangle, we found that we could express the area function as just a of x is equal to 3 times x. So then we did another example, and so this example was an area function where we were now doing the integral of t plus 1. So just to remind you, what's going on with this t and this x, basically they're each serving different purposes, right? So the x here represents the top bound of our integral. And so you're thinking of, because it's an area function, the thing that we're varying in this function is x. So like we said on the last one, you're kind of imagining that you can slide this top bound back and forth. So why are we using t for the part inside the integral? Well, if you really wanted to, maybe you could use x, but it would start to get confusing because you would have x representing two different things. So as I mentioned in the previous video, it really doesn't matter what variable you use inside of an integral. As long as this variable matches with what's here, the meaning will be the same. And so we're using t just to not be confused with x, so that we kind of, the t represents one kind of sense of a variable and the x represents something else. So in the previous video, this one was a little bit trickier. We had a little bit more kind of geometry to do. But we found that the area function could be written as x squared over 2 plus x. So I'll get to, in a moment, the examples that you did on the worksheet, but I want to start by making kind of an observation about both of these. So looking at this first one, I want to think about what happens when we take the derivative of a of x. So if we take the derivative of a of x, so the derivative of 3x is just 3. And notice that that is the same as the function that was inside of our integral. And that is not a coincidence. So we'll see that actually that's going to be how it works. We'll see that when you take the derivative of the area function, you're actually going to end up with the same function as you had inside your integral. The only difference, and we'll see this in the next example, is that the variable will switch to being an x instead of being a t. And so in this case, that didn't happen because 3 is a constant, so there's no variable attached to it. So that issue didn't really come up. But in this case, if we take the derivative of our area function, so the derivative of x squared over 2, we bring that 2 down, and it cancels out with the 2 in the denominator, and we're left with just x, and then the derivative of x is 1. So we have x plus 1. So this is the same as the function that is inside of our integral. The only difference is that, so if we're calling, so I guess I called this function h of t is equal to t plus 1, we would now call it h of x instead of h of t, because we're just switching the variable from being a t to being an x. But again, because the variable doesn't really matter, it's the same function. It's really communicating the same thing, right? H of x equals x plus 1 is the same as h of t equals t plus 1. So that is the fundamental theorem of calculus, and we'll write it down officially in a moment, but just to say it again in words, the fundamental theorem of calculus says that if you take the derivative of the area function, you get your original function that was inside of the integral, just with x as its variable instead of t. So before I write down the official version or the official statement of the fundamental theorem of calculus, I want to look at the two examples from the worksheet I asked you to do in the previous video. So in the, let me actually just move these up a little bit, sorry. So same kind of idea in this, in the worksheet. It was just that we then changed the lower bound, right? So in these two examples, notice that the lower bound was 0 here, and it was also 0 here. And then I switched it in these other two examples to be 1 as the lower bound in the rectangle example, and then 2 in this other example. So in the worksheet for the previous video, you should have found that a of x equals the integral from 1 to x of 3 dt, and a of x is equal to the integral from 2 to x of t plus 1 dt, you should have found that those formulas differ from the formulas above, so the ones that we found up here, a of x equals 3x and a of x is equal to x squared over 2 plus x. You should have found, sorry about that, that they vary just by a constant. And so I'll write down what you actually should have gotten in a second. But they differ from the above area functions by a constant. And so in this case, so for this first one, you should have found that the area formula for the integral from 1 to x of 3 dt, you should have found that that was equal to 3x minus 3. And really the reason for that is basically that you're just excluding this part here, right? And so this part has an area of 3, and so the area comes out to be the same as the area you got above, but just without that extra rectangle. And then this one was a little bit more complicated for the geometry, but once you did all the simplification and everything, you should have found that the integral from 2 to x of t plus 1 dt was equal to x squared over 2 plus x minus 4. And again, where does that come from? It comes from the fact that this extra piece that you're not including, if you count it up, this actually has an area of 4. But you could have figured it out, without making that observation, just by kind of looking at the geometry. So what is significant about the fact that these only vary by a constant compared to the area functions we found above? Well, what happens when you take the derivative of a function that differs only by a constant? You get the same result, right? So in this case, if we take the derivative, we still get 3. Right? Like this minus 3 part doesn't affect the derivative. And then same thing here, if you take the derivative of this area function, you still get, bring down the 2 and you still get x plus 1, and then the minus 4 doesn't affect anything. And so basically what I'm trying to show you with these two examples is that this lower bound does not affect the fundamental theorem of calculus. It does affect the area function, right? You got a slightly different area function, but the fundamental theorem of calculus is talking about the derivative of the area function. And the derivative of functions that differ by a constant is the same as the original. So maybe let me just make a note about that up here. So we said that they differ from the above area functions by a constant. So that means that their derivatives are the same. Okay, so now we're ready to actually write down a little bit more formally what the fundamental theorem of calculus says. So the fundamental theorem of calculus which is very frequently abbreviated as FTC. So I'll write that down. And as I mentioned before, this is part 1. So the fundamental theorem, I forgot to say, let me write it this way. I'll say FTC in parentheses. I think that was what I was trying to do. And then I'll just say part 1. Okay, so the fundamental theorem of calculus says that if you have an area function, so I'm going to actually use a capital F of x instead of a of x. It doesn't really matter what letter you use, but this letter is used a little bit more commonly in this context. So if you have an area function, so you have the integral, and I'm going to put a letter a down here because as we just talked about a moment ago, it doesn't matter what your lower bound is when you're taking the derivative. And so this number a could be 0, it could be 1, it could be 5, it could be -3. It doesn't matter what that lower bound is. So if you have an area function where you have something that you're integrating here, and we'll call that f of t, then what the fundamental theorem of calculus says is that if you take the derivative of the area function, so f prime of x, capital F prime of x, is going to be the same thing as the inside function, except for that instead of a t, it's going to have an x in it. And we saw how that played out in the last examples. It's basically because because the upper bound is x, x kind of gets involved, whereas that t was just kind of a placeholder. So let me kind of express this in words again. So this is basically saying, in other words, the derivative of the area function is equal to and I'm going to use a word that we haven't used yet, I don't think, so I'm going to just write it down and then I'll tell you what it means. So integrand is just a way to refer to the function that you're integrating. So integrand is just a word that means the function, I'll just say the function inside the integral. So it's equal to the integrand, but with x instead of t. So it's the same function that you have on the inside, but you're just using x instead of t as your variable. So another way of saying this that I want to write down as well, so going back to something we talked about at the beginning of the quarter, if one function is a derivative of another function, well, you can also restate that in terms of antiderivatives. So if the derivative of the area function is the function inside, another way of saying this is that the antiderivative of the integrand of the function on the inside of the integral is equal to the area function. And I feel like that's one of those things that might sound kind of confusing, but again, it's just this idea that like if one function's the derivative of the other, then you can say the same thing about antiderivatives. It's just backwards. So the derivative of capital F is little f, but with that variable switch. And then similarly, the antiderivative of little f is big F, again, with a variable switch. Okay, so let's look at some actual examples of how you might be asked a question to test this. So these questions, for the most part, are actually very, very easy. I think there's just, they look confusing. I'll put it that way. So these questions will, at first, when you look at them, they'll look very scary, but there's really not much you have to do. There are a few ways that we can make it more complicated, and we'll get to those examples in a little bit, but the basic examples of this are actually just very, very simple. So an example of how a FTC1 question might look is something like this. So you might say if capital F of x is equal to the integral from 5 to x of, and I'm going to write kind of a complicated function here. So sine of 5t plus 1 over t squared plus e to the cosine of t dt. And the question is to find the derivative, find capital F prime of x. So you might look at this and start to try to do something, if you've taken Calc 2 before, you might have some idea of how you would go about evaluating this integral. That is not what you're supposed to do in this problem. All you have to do to answer this problem is go back to what FTC tells you. So FTC tells you that the derivative of the area function is going to be equal to the integrand, the thing inside of the function. And so all we have to do is take that function that's on the inside and just replace the t's with x's. So basically we can just say by FTC1, capital F prime of x is equal to sine of 5x plus 1 over x squared plus e to the cosine of x. That's it. That's all you're doing is you're just taking the integrand, the function inside the integral, and just replacing the t with an x. So let's do one more example along these lines, and then we'll look at basically a slightly more complicated variant. So this is another way that you might be asked an FTC question. Again, it's not going to be a very challenging question, but just a different way of writing it. So let's say that we are asked to find the derivative of the following. So we're finding the derivative of the integral from -1 to x of t over 1 plus t squared minus e to the t squared dt. So what does it mean? Like this is a slightly different notation, right? We have d dx on the outside. Remember that d dx is just another way of saying the derivative with respect to x. So this question is exactly identical to if we had said instead, f of x is equal to, this integrand, or sorry, this integral, and then we're asked to find f prime of x. So it's just a kind of a shorthand. It's a way of expressing the same idea without having to say, to name the area function. So again, we just say, okay, by FTC1, the derivative of all of this stuff, so t over 1 plus t squared minus e to the t squared dt is just going to be equal to the integrand, so just replacing every t with x instead. So x over 1 plus x squared minus e to the x squared. And so that would be our answer. So just really try not to overthink these. These problems can look a lot more complicated than they are. Okay, so the next thing I want to talk about is a certain style of of FTC1 question where we have to actually use the chain rule. And so before we get into that, I just want to remind you what the chain rule is, so that when we encounter it in the context of these FTC problems, you'll be able to connect it to what you learned in Calc 1. So reminder, the chain rule. So how does the chain rule work? The chain rule is basically a rule for taking derivatives, right? And so what the chain rule says is that if you have a function, so I'm going to say if f of x can be written as a composition of g and h, so g of h of x, then how do you take the derivative of this composite function? Well, it has kind of two parts to it. So the first part is that you take the derivative of the outside function, so g prime of, and then you leave that same original input on the inside, so g prime of h of x. And then you multiply that with the derivative of h of x. So maybe let's do a quick example of this just to kind of refresh your memory on how it works. So for example, if we had the function f of x is equal to cosine of e to the x. So why is this a chain rule problem? Well, this is a composite function. In this case, the outer function would be, and usually when I write the outer functions, I like to use a letter other than x, just so that there's not too many x's floating around. So the outer function in this case would be g of u is equal to cosine of u. And the inner function would be h of x is equal to e to the x. So when we go and find the derivative of this composite function, the first part of the derivative consists of the derivative of cosine of u. So what's the derivative of cosine of u? It would be negative sine of u. But then instead of putting u there, we actually just put our original function back in, because notice it's g prime of h of x. So the inside function is still just supposed to be there inside the derivative. Then we multiply it by the derivative of h of x. And in this case, the derivative of e to the x is just e to the x. So we end up with this. Okay, so let's see how this plays out with a FTC problem. So let's say that we have, again, an area function. This time it's going to be f of x is equal to the integral from 1 to x to the fourth of sine of t dt. And so the question in this problem is going to be to find the derivative of this integral. So find f prime of x. So what is different about this problem compared to some of the earlier ones we looked at? Well, notice that in the original statement of FTC, the upper bound is x, and that's what has been the case in every problem we've done so far, right? It's only been, the bottom bound has changed, but the top bound has just been x. So basically what's going on here is we have a composite function where instead of just having an integral from 1 to x, we're having an integral from 1 to a function of x. So I want to start by identifying what that inside and outside function are, and then we'll see that when we use FTC, we basically just have to apply the chain rule. And I think, by the way, I think this is probably the trickiest part of FTC problems, and so don't be surprised if this next part feels a little confusing. I think once we get to what the answer is, you'll see, you'll be able to replicate it fairly, it won't be as complicated as it seems, but I want to make sure that I'm really explaining thoroughly kind of where the answer comes from. So that's why I'm going to be maybe going a little bit more into depth than you will when you're actually doing this problem yourself. Okay, all that being said, so let's get into it. So what I'm going to propose, I'm going to tell you what the inside and outside function are, and then I'll kind of show you how when we put them together, we still get this original, the original function. So let's let h of x, actually, let me say the other one first. So let's let g of u equal the integral from 1 to u of sine of t dt. So I'm basically just kind of changing this x to the fourth as with like a generic placeholder of u. And then let's have our inside function, h of x, be x to the fourth. So why did I say these two things? Well, what happens now when we compose these two things? So if we do g of h of x. So g of h of x is going to be the same as g of x to the fourth, right? That's just how composite functions work, where we're just replacing h of x with x to the fourth. And then how is this function going to work? Well, we're supposed to take whatever's inside the parentheses, according to the rule for g of u, whatever's inside the parentheses is supposed to then appear as this top bound. And so that means that g of x to the fourth is going to be the integral from 1 to x to the fourth of sine of t dt. And that's the same as our original function. So basically, we just showed that f of x is a composite function. So this area function we're dealing with now is a composite function, and we need to use the chain rule to find its derivative, to find f prime of x. Okay, so let's see how that's going to play out in this case. So the derivative of capital F of x is going to be, according to the chain rule, it should be g prime of h of x times g prime of x, right? Because that's just how it works. That's how the chain rule works. Okay, so what is g prime? So g of u is just a normal area function, right, where we just have a u instead of an x. And so g prime of u is just going to be the integral, is going to be, so to find g prime of u, we're just going to use like regular plain old FTC1, right? Because g of u is just a normal area function. And so g prime of u is just going to be the integrand, right? Like it's just going to be that inside function. Is everyone with me? I know that this is a little confusing because there's a lot of different functions floating around. But again, because g of u, forget about the fact that it's a u, it's a regular area function. We have an input variable here, we have the same variable here, there's nothing funny going on. So the derivative of the area function is just going to be equal to the integrand, except for that we replace the t with u. However, when we use the chain rule, you're not supposed to put a u here, you're supposed to put your original inside function in. So what is h of x? H of x is equal to x to the fourth. So we're going to say sine of x to the fourth. So basically the first part of this derivative is, it's like we're taking the original integrand, but we're replacing the t, not with x, but with x to the fourth. And then the second part of the derivative, according to the chain rule, should be the derivative of the inside function. And so the inside function, and sorry, I just realized I wrote something wrong. I hope this didn't confuse you all. So this should have said h prime of x. Sorry about that. So again, just in case anyone's confused, this is just the chain rule, right? The chain rule says g prime of h of x times h prime of x. Sorry about that. So this should have said h prime of x. So the last step of the chain rule is that we just take the derivative of h of x. And so what's the derivative of h of x? It's 4x cubed. And so our answer for this problem is this. It's sine of x to the fourth times 4x cubed. So, where did this answer come from? It came from the chain rule. If you find all of this confusing, writing down all this stuff, I think it's not too hard to kind of figure out where your answer came from without using the chain rule. So going back to our original problem, basically all we did is we applied FTC the same way that we normally would, except for instead of replacing t with x, we replaced it with x to the fourth, right? So that's why we got, instead of just sine of x, we have sine of x to the fourth. And then the only extra thing is that we had to then multiply by the derivative of this upper bound. So if you're looking for kind of a shortcut and you don't want to write down all these different functions, you can basically just apply FTC, but instead of replacing the t with an x, replace it with whatever that top bound is. And then you just multiply by the derivative of that top bound, because that ended up being the inside function in the chain rule. So that's our answer. So there's one more thing I just briefly wanted to bring up just to kind of make a connection to yesterday's video now that we have FTC. So now we know that the derivative of the area function is the same as the inside function, right? And so I want to go back to this question we had in yesterday's video about finding local maxima and minima. So remember that in yesterday's video, we talked about finding, so we called this area function a of x. So let me maybe write that stuff down. So let's call this function f of t. And we had the area function a of x is equal to the integral from 0 to x of f of t dt. And in the last video, we found that a of x has a local min at x is equal to 8 and a local max at x is equal to 2. So why was that? It was basically because of this idea of adding up area and this kind of contrast between the positive and negative area. So here we had positive area, but then as soon as you cross past this 2, you start accumulating negative area. And so that means that the area function is increasing during this first portion, but then it starts decreasing. And so that's why we ended up having a local max at x equals 2, because our area function stopped accumulating new area and started actually going down. Whereas the local min, well, that happens because, again, so here you've accumulated area. At this point, you actually have more and more negative area, but then you start actually adding in positive area again. And so x equals 8 is that place where you make the transition from, just adding in more negative area to then actually accumulating positive area. So that's where the area function is going to stop decreasing and start increasing again. And that kind of a shape gives you a local min. So the connection that I just wanted to make, now that we kind of know this relationship between the area function and the integrand, so the derivative of the area function is the integrand, right? And so I just want to remind you of something from Calc 1, which was that, remember, if you're looking at the graph of the derivative, you can figure out what the local maxes and mins of the original function are by looking for the places where this function, the derivative, crosses the x-axis. So if you took 151 with me, there was actually a question very similar to this on our final exam, where I gave you a graph of a derivative and I said, looking at this graph of the derivative, what are the local maxima and minima, or at what x values do the local maxima and minima of the original function happen? And so what you would say is, okay, well, in order for there to be a local max or min, the derivative needs to be equal to 0. And so notice the derivative is equal to 0 at these 2 points. Because again, the derivative of this function is this function. So what we're looking at here is really the graph of the derivative of the area function. And then how do you figure out whether something's a local max or min? Well, remember that when the derivative is positive, that means that the original function is increasing. And when the derivative is negative, that means that the original function is decreasing. And so if you have a situation where your function is going from increasing to decreasing, that's going to give you a local max. And when you have a situation where a function goes from decreasing to increasing, that's going to give you a local min. So I just wanted to kind of point that out, that there's really 2 ways to answer this question about local maxima and minima. Personally, I think the thinking of adding up the areas is a slightly easier way to think about it, but I just wanted to make this connection because, you know, it is valid to think of this graph now as the graph of the derivative and to interpret it the same way that you would in Calc 1. All right, so that is it for today. As I mentioned, in the next video, we'll be getting into FTC2, which is going to be a really useful tool. It's going to really open up what we can do in this class and allow us to evaluate all sorts of different types of integrals.